Hi everyone, this is Sachin Kumar, PhD student from Department of Material Science and Engineering, IIT Kanpur, working under the supervision of Kaustubh Kulkarni. So, as I told that, my current research topic is diffusion in nickel-based superalloy. This is my third video lecture in Material Science and Engineering, and in this topic, I have taken the microstructure development of iron carbon alloy. At previous video lecture, we have seen the phase diagram of iron carbon diagram. So in this video lectures, some of the important microstructures development will be we are observing. We will, as usual, we will start with the overview of our video lecture. So small recap on eutectoid steel. So we will get to know. I have already explained what is eutectoid steel in a previous video lecture. So a small recap I will do in this lecture. And second thing is very important point of our focus is formation of pearlite. Formation of pearlite. So how this pearlite will be formed? So what's the mechanism behind this one, pearlite formation? Everything we are seeing in this video lecture. So after this, a microstructure development in hypo as well as hypereutectoid alloys we are observing. Finally, we are concluding this video lecture with a numerical problem. So we are numerical problems will be there. With the help of this phase diagram, we can solve very easily. That is tie rule, tie line, as well as lever rule concept are introduced in this video lecture. As I said, we will start with overview. Summary of eutectoid steel. So this is a composition 0.77. So from where it is taking into this is a eutectic composition. So from where austenite is transformed into the pearlite. This reaction is called as eutectoid reaction. That is, gamma is transformed into alpha ferrite plus Fe3 cementite. Both commonly called as pearlite. Pearlitic formation. So this is a brief summary of eutectoid reaction that we have seen in the last video lecture, that is video lecture 2. So now we are seeing in depth. So as if we form the pearlitic structure, we have to see more in depth about the formation of pearlite. So this lecture is divided into four main subsections. That is a pearlitic formation. So what's the mechanism behind this formation of pearlite, and kinetic transformation of pearlite, and there is an interlamellar spacing, how it will be affected with the temperature. Yes, we are seeing in this video lecture. So as we see that gamma is having 0.77 weight percent of carbon, and here alpha is having 0.02, which is almost pure iron, and Fe3C is reaching 6.607 weight percent. So we are seeing this reaction, the weight percent of carbon is changing tremendously after transforming into the pearlite. One is carbon deficit phase and one is carbon rich phase. This can be happen only when we are reducing the temperature below lower critical temperature. A1 temperature we can call. So when we are reducing temperature below A1, there is a redistribution of carbon takes place. Due to this redistribution, one will become carbon rich phase, another will become carbon deficient phase, that is alpha and Fe3C. This is due to the diffusion of carbon. Due to the diffusion of carbon, redistribution will take, and this redistribution will result in the formation of pearlitic region. So now we have seen how the pearlite is formed. We will have intro to pearlite. Now pearlite is having 88% of ferrite and 12% of cementite, and this will play a very major role in the mechanical properties of steel. Mechanical properties of steel, and we can see from the microstructure, this is a continuous phase and this is distributed in the ferrite as the ferrite will as a continuous phase and this is a distributed phase. Now we have seen the pearlitic transformation, how these pearlites are formed and what are the main phases and the constant and the weight percent we have seen in this pearlitic transformation. Now we are getting into the mechanism of transformation. So we have seen that it is having two phase. Mechanism. We know that it consisting of ferrite and cementite. Right? So now it's an alternate layer as we seen from the microstructure. One question will arise: which phase will nucleate first? So within these two, So whichever will nucleate first, that's called as an active nucleus. Active nucleus, that is called as an active nucleus. Some model has been proposed till now, but best model till now we are considering FC Hull and RF Mel. Don't know how to pronounce this one. H is there. HC Hull and RF proposed one theory for the formation of Pearlitic region. According to them, a cementite is an active nucleoside. That means cementite will nucleate first. From there, the ferrite will grow, and as well as cementite will grow togetherly as in the form of the lamellar structure and forms the Pearlitic region. We will see now. So how this mechanism is explained by these two guys. According to them, the lamellar structure, that is alternate layer of cementite and perlite, will be formed by nucleating cementite first, then it will goes into methyl ferrite. Due to the diffusion of carbon, when we reduce the temperature below the eutectoid temperature, there is a diffusion of carbon. Diffusion of carbon will take place at the grain boundaries of austenite. This accumulation will result in the increase in the concentration of carbon and results in the formation of Fe3C. Due to this diffusion of the carbon, adjacent so due to this is a grain boundary and this is first Fe3C that is formed. It will grow. After this growth, there is a deficiency of carbon here. I will make another color here so that it will be easy for us. Adjacent to this one, there is a deficiency of carbon. This carbon composition will be less, nearly equal to 0.02. That means alpha ferrites are formed adjacent to this one, but at the grain boundaries. They will grow along with the Fe3C. This results in the formation of alternate layer of, here again it will result in the, again here it will Fe3C will develop, but in between these two ferrite will develop. This is an alternate layer and this will result in the formation of colony in one particular directions. After that they will grow in another direction. So this is how the austenite will transform into perlite. This is Fe3C. In between these two, it's alpha. This is a mechanism, simple mechanism that have been explained. After this, we are we will move into the next topic, that is kinetics of transformation. This kinetics can be explained with the help of kinetics of transformation. Kinetics of transformation. We can be explained this kinetics with the help of a thermodynamics parameter called free energy. At A1 temperature, free energy of it can be denoted with the help of G. At A1, free energy of gamma is equals to free energy of perlite. Because of this one, it will take infinite time at A1 temperature. It will take infinite time to transform austenite to perlitic transformation, perlitic structure. In other words, we can say transfer perlitic formation, it won't happens at A1 temperature. It won't happen at A1 temperature. When we reduce the temperature below A1, free energy of perlite will reduces and free energy of gamma compared to free energy of gamma. This will result in the formation of perlites. If the free energy is reduced, then we can say perlites are more stable, more stable than austenite. Because of this reason, austenite will convert into perlite. Stability is explained with help of Gibbs energy. As we this is happened below T should be below A1 temperature. This means this indicates that as we reduces this indicates that as we reduce temperature, transformation rate will increases. The rate of austenite to perlite transformation will increases with the lowering transformation temperature. From the graph, so we can plot a graph also for this one. This is temperature in degrees Celsius, and decomposition, that is a perlitic formation. Increases. This is the one line that we have got. Second things we need to observe that we are reducing a temperature. This means that a diffusion of carbon will also reduces, but the paralytic transformation is driven by carbon diffusion itself, a rearrangement of the carbon, as is said in the previous slides. This will have the negative effect. Diffusion of the carbon will have the negative effect on the formation of perlite when we reduces the temperature. Hence, the plot will be like this. So this is temperature in degrees Celsius, and this is the perlitic formation. Perlitic formation. By combining these two concepts, by combining these two concepts, one with thermodynamics point of view, another is with diffusion point of view, then we can say the overall effect is like this. Overall effect. This is due to diffusion and this is due to thermodynamics. Overall, it will be like this. So initially, when before reaching this peak, thermodynamic parameter will dominate. After this, diffusion parameter will dominate. This can be explained. This overall can be explained as we reduces the temperature. Initially, the transformation rate will be increases and it will reaches to maximum point due to thermodynamic parameters. Thermodynamic parameter called such as free energy. So again, the transformation rate will reduces. This is because when we reduces the temperature, the diffusion of a carbon will reduces significantly. This results in the reduction of the transformation of perlite. This can be explained very easily. Now we have seen kinetics of transformation, which results in the formation of thermodynamics as well as diffusion. Last is interlamellar spacing. This is a interlamellar spacing. How this will affect? So we can vary this one with the help of temperature. Transformation temperature. The lower the transformation temperature, the smaller will be the interlamellar spacing. The smaller will be the interlamellar spacing, the stronger will be the steel. The strength of the steel is increased. That means as we reduce the transformation temperature, the strength of the steel will increases indirectly. This is the importance of lamellar spacing. This will affect the mechanical properties of a steel. We will start with the next video. Next slide is microstructure evolution in hypo and hypereutectoid steel. This figure will explain clearly about microstructure evolution. First of all, we will start with hypo, then we will switch on to hypereutectoid steel. So, as the name indicates, hypoeutectoid steel hypoeutectoid steel has a composition less than 0.77. Name will indicates this is composition of eutectoid. Hypo means lesser, that's 0.77, less than 0.77 weight percent of carbon. First, second thing, when we have a temperature here, we will start with this temperature. Here it's having completely gamma structure because it's in a gamma phase. At about 900 degrees Celsius, it's having completely gamma structure. When we are reducing this temperature to this A point, this is a point. Consider this is a B point. When we are reducing a temperature from A point to B point, it is the alpha will starts to nucleate at the grain boundaries of gamma, and hence alpha as well as gamma will coexist. And when we are considering this point, so when we are considering this point, for example, consider this is the C point, okay, and we can know the composition of alpha and as well as a gamma by drawing a line. There is a tie line. As we reduces the temperature from here to here, here to here, the composition of alpha is increasing, and whereas gamma is varying along with this line. When we are reducing point C from point C to point D here, it's a lesser than A1 temperature, lower critical temperature. This results in the formation of Pearlite structure. But the alpha ferrite which is formed here in these regions will stay as a pro-eutectoid alpha. Alpha ferrite. But the remaining austenite, here austenite will be there, right? So this will transform it into Pearlite. This is the microstructure, final microstructure of pro-eutectoid hypoeutectoid alloy steel. This is the microstructure of a hypoeutectoid steel. Okay, let's begin with the hypereutectoid steel. As the name indicates, hypereutectoid steel means composition will varies from 0.77 weight percent to 2.18% of carbon. This is a composition of hypereutectoid steel. That means this is eutectic compositions. Greater than eutectic compositions within 2.4 is called as hypereutectoid steel. We will start the hypereutectoid steel cooling. Because of that, we have considered the 1.2 weight percent of carbon, which is under hypereutectoid alloy. We will start with a A1 dash at temperature of 900 degrees Celsius. It is having a single phase austenite, gamma austenite. From here, if we are reducing the temperature to 780 degrees Celsius or 80, 50 something, it is having two phase structures. There is a gamma is there, austenite is there, as well as at the grain boundaries of austenite, Fe3C is nucleating and it's growing along the grain boundaries of gamma. And the composition of this gamma is varying along this line. This is O and this A, capital A or P. So composition of austenite will vary along a line OP as we reduces the temperature. When we will move from this B dash to C dash temperature, this is a C dash temperature. This C dash temperature is less than critical temperature, is A1 temperature. Because of this, there is a formation of perlitic region. This is a perlite and this is Fe3C. So Fe3C is completely at the grain boundaries and the remaining retained austenite will transform into perlite, which is having alternate layer of cementite plus ferrite. This is a final composition microstructure of the hypereutectoid alloys. A main difference hypo and hypereutectoid alloys is first of all composition, sorry. Okay, finally we will have a overall summary, that is the difference between hypoeutectoid steel and hypereutectoid steel. I have categorized in three categories, that is a composition, microstructure, mechanical property. First of all, composition will vary. For hypoeutectoid steel, it is less than 0.77, and for hypereutectoid steel, it lies between 0.77 to 2.14. But usually in our industries, they are considering only 1.58% or something else. And whereas a final microstructure that we are obtained for the hypoeutectoid steel is proeutectoid ferrite at the grain boundaries and along of perlitic region. And whereas hypereutectoid steel consisting of proeutectoid cementite, which is network-like structures, plus perlitic region. The mechanical properties. As these mechanical properties are mainly depends upon the microstructure of the alloy. Since this hypoeutectoid steel consisting of proeutectoid ferrite, they are more ductile when we will compare with the hypereutectoid steel, because they are consisting of proeutectoid cementite, which is intermetallic first of all, and it's a brittle in nature. This is the main three differences between hypoeutectoid steel and hypereutectoid steel. So this is all about the differences between hypoeutectoid steel and hypereutectoid steel and microstructure evolution. Now we are jumping into the next slide, that is numerical problems that we are facing in upcoming videos. For that one, I am explaining some basic concepts that will be useful for the next videos. From the phase diagram, this is a phase diagram of iron carbon diagram. From here, we are calculating two main important things. First of all, composition, composition of phases and weight fraction of phases. Weight percent calculations for the phases. Here, first of all, from to calculate the composition of the phases, we are using tie line. So consider this is a tie line. Okay, so this is alpha phase. If you want to calculate the composition of alpha in eutectoid state, so this is a point of eutectoid, right? So we need to calculate the alpha phase. It's consisting of alpha as well as Fe3C. So for calculating of alpha, for composition of alpha in eutectoid at this temperature T, we are just drawing a straight line at this temperature and we are considering this composition as well as this composition. That means alpha is having 0.02 weight percent of carbon and Fe3C is having 6.670 weight percent of carbon at this temperature T. One more time I will draw it. First of all, composition. Alpha composition can be obtained by drawing this tie line AB, and this is 0.35 weight percent of carbon and Fe3C composition is 6.67 weight percent. This is composition can be calculated with the help of tie line, right? So when we are considering weight fraction of each phase, then lever rule is applied. So I will tell. So what is lever rule and everything. So weight fraction of alpha can be calculated. This is 0.6. Alpha can be calculated CB divided by AB, and weight fraction of Fe3C can be calculated AC divided by CB. I will tell you. This is alpha phase, this is gamma, alpha plus gamma, and this is Fe3C. So right. So we are calculating the composition. That is, we are just drawing a straight line and we are projecting downward towards the composition axis, and we are measuring. We are observing what is the composition. This is very easy, tie line. Whereas in lever rule, we are considering this point, right? So if you want to calculate the alpha composition, we have to take the distance between opposite thing, right? CP divided by whole length. Then we will get the fraction of alpha. And whereas for Fe3C, Fe3C is this side. We have to take the opposite length AC divided by AB. This is how calculate. Similarly, we are calculating for the hypereutectoid state and hypoeutectoid state. We can calculate the Pearlite concentration as well as hypoeutectoid, proeutectoid, and pro-eutectoid ferrite and pro-eutectoid cemented percentage in a which comes under hypo and hypereutectoid still respectively. When we will take the numericals on this one, we will know in detail about the calculation. For simplicity, I will explain for the hypoeutectoid steel, right? This is a composition we are considering, that is C composition, and this is 0.02 and this is 0.77, right? Okay, this is alpha, alpha plus gamma. Okay, this is gamma and this is FHC. Here at this one, it's having first of all pro-eutectoid ferrite and pearlite. We need to calculate the composition of both the things. First of all, pro-eutectoid ferrite composition can be calculated by drawing a tie line here. This is the thing, and here it is. We are not going beyond this one, so up to here. This is a pro-eutectoid ferrite composition. This is almost less than 0.022. This is 0.01, consider it is. And whereas for the pearlite, the composition is 0.77. So for the weight fraction is A, B, this C. Weight fraction is very important. Weight fraction of pro-eutectoid ferrite. That is formula comes under BC divided by AC. Correct? Yes. For the weight fraction of pearlite, can be obtained AB divided by AC. Now we got weight fraction of pro-eutectoid alpha as well as pearlite. But we are seeing it consisting of alpha ferrite, pro-eutectoid ferrite, and pearlite is also consisting of ferrite plus cementite. Because of this, we need to calculate the total composition of ferrite and total composition of cementite. To calculate the total weight fraction, first of all, ferrite A, B, C, here it is D, right? We have to consider a whole length. Before that one we are considering up to here, but now we are considering whole length, right? The weight fraction of total ferrite can be calculated. We are considering this is a composition. We have to consider this B to D length divided by A to D length. Whereas for the total composition of cementite is having, this is AB divided by A to D. This is a main total weight percent is a main thing that we have to observe. So in many of the gate exams, they will ask these questions only, and many of the students will get confused between protected ferrite and the total weight percent of the ferrite. We read the question properly and calculate it and get the answers. I will I will take some few numericals in the next upcoming video to solve this question, phase diagram. Those questions will be asked in gate exams and other competitive exams. Thank you.